One of the most popular sequential circuit design problem is to design a sequence detector. Sequence detector is something like this kind of system where clock is there because this is a sequential circuit. The given bit stream of inputs. So you receive a 1 0 1 1 1 0 at every clock tick you receive a one single bit, and then output produces a 1 if it detects a certain bit pattern. So what I mean by that is as follows. So input towards the input X, a stream of bits are provided. So very first you get 1, 0, 1, 0, 0, and the like. At every clock tick, one single bit is entered into the system. Then based on that, you should produce output once you detect a certain pattern. Suppose we want to detect 101 as a pattern to detect. The very first clock tick, 1 is produced, 1 is entered, but we don't detect the 101 pattern yet, so output is 0. Next bit, still we don't detect the pattern. And third bit, 101 has entered, so we have detected the pattern. And then 0, no pattern after that, 0, no pattern after that, 1, no pattern, 1, no pattern, 1, no pattern, 0, no pattern, 1. Now we have detected the 101 pattern. So as soon as you detect the 101, then we say this pattern has detected. In this case, if this bit was 1, then the output should be 1 as well, because up to that we have detected 101 as well. So the first step of sequential circuit design is a construct a state diagram. Then the constructing state diagram is the most critical part of the sequential circuit design. If you construct the state diagram correctly, the rest of the steps are pretty straightforward. So this is the most creative part of a sequential circuit design. So when you construct a state diagram, what you need to figure out is a number of cases that system should remember. That is the thing we need to figure out. So in this example, if the system remembers all input bit streams, 101 and whatever, then the system should correctly say whether a bit pattern has detected or not. However, the problem with the remembering everything is if we have so many bits, millions of bits comes in, billions of bits comes in, then for the system to remember that many bits, this requires too much memory. Sometimes it's impractical to have such a large memory to detect the bit pattern. So that's not practical. So what would be then the minimum number of cases the system should remember? Based on that, we can minimize the memory. As an example or illustration, how do we find such number of cases that should be remembered is as follows. Suppose you are classifying three shapes. So in every clock tick, one of the three shapes, circle or square or triangle, comes in one by one, and your job is to classify that into three big boxes. Here put circles only, squares only, triangles only. Then every clock tick, one of the shapes comes in, then you need to remember three different cases of shapes you are expecting, and based on the shape, throw in into proper boxes. So what you need to remember, three cases you need to remember in doing your job. So go back to the original sequence detector. Then this 101 sequence detector, what has to be remembered? What is the minimum number of cases that the sequence detector should remember is as follows. So instead of remembering all bit streams, so first to find it out, suppose you are the sequence detector in the box. So you will receive one or zeros at each clock tick. Then you say whether this pattern has been detected or not by raising your hand on Y output. Then what is the minimal thing, minimum number of cases, different cases that you should remember. Instead of remembering all the bit patterns, what you need to remember is the minimum number of cases. So to find this out, we can do a small simulation, assuming you are the sequence detector. Then just imagine closing your eyes and imagine that one bit information per clock comes in, like 1 0 0 1 0 1 and the like. Then how do you detect the bit patterns? By remembering something minimally. That is, you could just remember cases like that. In cases number 1 or case 0, say there's the bit pattern 101. The first bit is 1. It's no bit pattern gets started yet. So you have received a 0, not first one yet. And then case 1 should be the beginning bit of the pattern. 1 has been entered. Just remember that. And then next case is 1 and then 0 has been entered. Then out of those three different cases, you should be able to respond correctly whether bit pattern has entered or not. So suppose you are in this state, 1 and the 0 are entered, have been entered. Just remember that at this moment, if another 1 enters, then say that bit pattern has detected. If it's a 0, then it's not the pattern. So if a 0 comes in, then go to the case 0. The bit pattern has not been started yet. So you are just remembering you are in case 0. Once you are in case 0, if 1 is entering, then you just say that I'm in case 1 now. If in case 0, 0 is entering, then just remain on the same case. The bit pattern has not started yet. So if you are in case 1, so remembering that I'm in case 1, at that moment, if 0 enters, then I'm moving to case 2. 1 and 0 has been entered if 0 enters. But if 1 comes in, then this is another start of the bit. It's not moving to any other case yet. So by remembering which case you are in, then based on inputs 1 or 0, you can either make transition to case or just remain. And based on that, you can detect a certain bit pattern. So that's the idea of a state diagram. Case A, number of minimal cases, you should remember that. So based on that, let's create a state diagram. So our goal is 101 sequence detector, and then we have 3 cases. So let's have it state as a case. State 0, the bit pattern has not started yet. State 1, the very first bit has been received, and state 2, 1, and then 0 has been received. And then at this moment in state 2, if I receive 1, I say I've detected a bit pattern. So let's draw state diagram. So since we have 3 states, we draw 3 circles. Circle represent states. So this is state 0, state 1, and state 2. And then depending on inputs, we make transitions and produce output. So if you are in state 0, nothing has been started yet, but if I receive input 0, then again that does not begin with any bit pattern yet, and the output should be 0. But if I receive a 1 as an input, then I'm making transition to state 1. But output 0 means pattern 101 is not detected yet, but I make a transition to state 1. In state 1, if I receive a 0, then I'm moving to state 2, 1 and then 0. But here, if I receive a 1, then it just remains on the same state, the 1, and then output is still 0. So I have a 1 but if another one comes, that's just start of the bit pattern again. So it's not next pattern yet, so remains there. In state 2, I've received 1 and then 0. Now, if I receive a 0, then 1 0 0 means not part of the pattern, so I need to go back to the very first 0. It's like that. So it's a completely voids the pattern. But if I receive a 1, then it is a output 101 pattern is detected. Then which state I should go? If I at this moment I have a 1 and then 1 received, then this one could be beginning of the pattern as well. So make a transition to state 1, which is a beginning of the pattern 1, and then finally output is 1. So the new one just received is a beginning of a next 1 1. It could be beginning of a next 1 1 pattern. So that is the state diagram constructed from the problem description. And then next step is to design state table out of a state diagram.